Hey, everybody. So we're going to continue talking about limits at infinity. We talked about a couple different kinds yesterday. I've got the first couple kinds written right in here. We say the limit as x goes to infinity of f of x equals L. Right? This is the idea that this function, as we let x keep growing without bound, it just keeps getting bigger and bigger, more and more positive, that the function itself is getting arbitrarily close to some number. That number we represent with L, the limit, right? So that's the idea with functions that approach some number, right? Same thing with negative infinity. As we let x get really, really negative, does the function approach some number? This is the situation when we have asymptotes, right? These are these horizontal asymptotes, to be more precise. Right? These are not the case for vertical asymptotes. Are different. As x approaches the number, the function approaches infinity. This is the reverse of that, right? Really, I should say the inverse of that. X approaches infinity, the function approaches a number, okay? We also looked at that sometimes we can have something like this, the limit as x goes to infinity of f of x equals infinity, or the limit as x goes to infinity of f of x equals negative infinity. Maybe the limit as x goes to negative infinity of f of x equals infinity, or the limit as x goes to infinity to negative infinity of f of x equals negative infinity. These are all statements to say the limit does not exist, but we're still telling you something about the function, that as x gets really, really positive or really, really negative, right? If we're putting in larger and larger positive x values, the function itself is either spitting out, in the case of a limit of infinity, the function itself is spitting out values as large as we want. There's no limit to how high we can make those values, or how big negative, right? So that's what these limits are about. Just to let us know the function never settles down and never stops growing or growing in the negative direction. It just keeps going forever. Okay, it's as large as we need it to be. Okay, so those are the two, these are the basic kinds of limits at infinity. We also developed a couple of rules that we're going to continue to use. So I want to remind us of those. We looked at the graph and did a little bit of thinking about the function 1 over x, both at as x goes to infinity and negative infinity. And in both cases, we realized we can make this function as small as we want, as close to 0 as we want, by simply taking x to be large enough. We used our limit laws in combination with this observation to write that, let's say if r is greater than 0, and we can really only show it for rational numbers. It's not going to matter to us. It will be true either way, but we should put that r is rational in order to use the limit laws that we have. But the big point is that we know if r is a positive number, the limit as x goes to infinity of 1 over x to the r is equal to 0. And the limit as x goes to negative infinity of 1 over x to the r is also 0. In this second case, we have to say provided, something like provided 1 over x to the r exists for negative numbers, right? That this expression makes sense, right? So the obvious example is if r is 1/2, it's positive, it's rational, but as we take the limit as x goes to negative infinity, we're putting negative numbers into the square root. We're only dealing with real numbers, no complex numbers, so we can't have that. So this limit makes sense as long as we don't run into that problem, right? So if we have a cube root, for instance, it doesn't matter and it'll still go to 0. Okay, so those are some nice rules for us. We want to look at a few particular functions. Well, we'll look at their graphs. I'm going to write down what I want to say first, and then we'll look at the graphs to see, to say a little bit more. So we're going to look at power functions. All right, so these are just functions of the type ax to the n. And I'm going to insist right now that n is a integer. Okay, so we're gonna look at our classic polynomial. These are the building blocks of polynomials, these little power functions. So if we were to look at the limit as x goes to infinity of ax squared, we get infinity. And if we have the limit as x goes to negative infinity of ax squared, it's also infinity. This is provided that a is positive. Okay, so I think this is easy enough to see, right? We're putting in larger and larger numbers, squaring them, multiplying them at a positive number. It's going to just keep getting larger. Even if we put in negative numbers and square them, they come out positive. And if we're getting larger numbers, right, further away from zero, those numbers are going to be huge. If we take a to be negative, this simply reverses. Right? Because now we've flipped all those parabolas upside down. Okay, and we'll look at a graph in just a second. Just want to make one more statement. Let's look at the limit as x goes to infinity of ax cubed and the limit as x goes to negative infinity. Let's consider these for a second, and we'll start out again thinking that a is positive. Well, if you take larger and larger positive numbers and cube them, you get larger and larger positive numbers, and whatever you're multiplying by them by, even if it's a fraction, makes it smaller, but as you get larger, it's still getting larger overall. And so this goes off to infinity. In the opposite direction, putting in larger negative numbers, the cube produces more negative numbers. And so we get the same thing, except everything's negative. Okay, this is, of course, if a is positive. And then if a is negative, everything is reversed, right? We're flipping over that classic graph of the cubic function that we'll look at in just a second. This is if a is less than 0. Okay, let's take a look at a graph of all these ideas. Whoops, this one is what we want. So here's x squared, right? Here's a graph of x squared with a equals 1. If I change a, right, so the red graph is a squared. Let's make this just a little bit easier to see, I think. Right, the red graph is a squared. The blue graph, I'm putting various values of a, the coefficient in front. Right here, we're at 5a, right? It just makes it narrow, but still both sides of the graph are going to infinity. On the other hand, if I start making a negative, it flips it upside down, and now everything, no matter which way we increase x, we go towards negative values. Okay. Now here's something interesting. Now I'm going to look at higher even powers, right? So we're starting with a squared. The red graph will be a squared, but the blue graph is now a to the 4th, and then to the 6th, and the 8th, and the 10th, and on up to the 20th, right? Obviously, they're different graphs. It's much steeper. It's flatter at the bottom and steeper once we get outside of -1 to 1. But it's the same shape in terms of what happens as we leave 0. To the right, we go to infinity. To the left, we go to infinity. And so, right, even changing that a, I'm just making it skinnier. And if I multiply by negative, the same thing happens. They flip upside down. So it turns out that everything I wrote here about ax squared is true if this exponent is any even exponent. So if it's an even exponent and positive, we're talking about positive even exponents here, these limits are true. Okay, so we get that for all of our even positive exponents. Let's look at our odd graph. Oops, let's turn that off. Let's make this x cubed. So there's x cubed, right? This is what we said. To the right, it's going to infinity. To the left, it's going off to negative infinity. Let's make a equal to 1. Let's put an a in here. It doesn't matter. Here, I'm just showing what happens with different values of a. Oh, I have n up too high. That's why this isn't making sense. Sorry. There we go. Now our blue graph is at a cubed, x cubed. They're both x cubed. And now if I change the value of the coefficient, we see it stretches it, but it still goes positive and negative infinity in the same way. But if we change a negative, it's flipped it over, right? Further, so that's changing the coefficient in front, what I called a. Now it's positive again. If I change the power, right? So here we're looking at x cubed. Let's go to x to the 5th, to the 7th, and so on. The same sort of thing happens. The directions are still the same. To the right, it's positive infinity. To the left, negative x. It's going to negative infinity. It gets extra flat though and extra steep, but the limits still apply. And if we multiply by negative, we still get that same flipping, okay? And so all of these rules that I wrote for the cubic function, cubic power function, these apply for all odd positive powers, okay? So that means we understand all power functions, right? We can understand all power functions and what they do at their end behavior, okay? What happens though when we start combining some of them? Let's look at a couple of these functions. So we'll start with 5x squared minus 20x. Let's first look at it algebraically. So we're looking at y equals 5x squared minus 20x. Let's look at the limit as x goes to infinity of this polynomial. Well, what we've got is something, if we remember what we just looked at, right? This, well, here, I'll just write it out. Let's do this. The limit as x goes to infinity of 5x squared minus the limit as x goes to infinity of 20x. Here we have an even power function, 5x squared. So we know from the work we did above that this is equal to infinity. Here we have an odd power function, right? There's an exponent of 1 right there. And we know from the work we did above, this goes to infinity, but then we've got a negative in front. So we get infinity minus infinity. And we are tempted to write 0, okay? But this is nonsense. Infinity is not a number. We don't have a definition. We're not working with a definition for how to subtract infinities, and it gives us the wrong impression in this case, okay? What this is another indeterminate form. We don't know what this means. Sometimes you end up with limits like this, and the function itself might approach infinity, it might approach negative infinity, it might approach 0, it might approach any number. So we have absolutely no new information from this, other than we need to try something else, okay? So we're gonna have to try a different method for taking this limit. We didn't find out that the limit didn't exist or anything like that. We just found out that the thing we tried to find the limit doesn't work. So I'm going to try something else. I'm going to try factoring out 5x squared from this polynomial, right? So when I factor 5x squared out of 5x squared, there's just a 1. When I factor it out of 20x, we get 4 over x, okay? Now, just all you have to think to see why this is true, multiply 5x squared times 4 over x, and we get 20x, right? We also have introduced an x in the denominator, which we want to think about because zeros, we've introduced the possibility of a 0, except I don't care about 0 because I'm looking at infinity. So for large numbers, there's no problem doing this. These are exactly equivalent statements, okay? Now I'm going to use my limit laws. I've got the product of two things. I can take their limits separately. Okay. Let's do the limit on the right first. The limit as x goes to infinity of 1 minus 4x. I'm going to do this off to the side because we're going to do this by separating this into two limits. That's one of our limit laws. The first limit is just saying what happens to the number 1 as x goes to infinity? Well, nothing happens to it. The second limit, I can pull a 4 out. That's one of our limit laws. We get 1 over x, and we'll of course know that this one is 0, and so this whole limit is 1. So this piece of this is just 1. This piece from the work we did just above is infinity. Infinity times 1, we can decide is infinity. The reasoning is this. We're saying that this piece here is growing as large as we want. Okay, we can make it as large as we want. This piece here is a number that's very close to 1. Multiplying large numbers by numbers very close to 1 still gives me large numbers. So this limit still goes to infinity. Okay, and okay, so there's our limit for 5x squared minus 20x. Let's look at that polynomial, right? And so we see what happens when we have, it looks a lot like a parabola. It's just shifted a little bit, but still as we go further away, we get those limits. That to the right, it's going to positive infinity. To the left, it's going to negative infinity. Let's do this next one, and then we'll make a little bit of a pronouncement. So we've got negative 7x cubed. Let's do this. Whoops. Sorry about that. Let me just write it down and then we'll work with it. So now we're looking at y equals negative 7x cubed plus 25x squared plus x plus 3. Okay. So now let's take this limit. We have the limit as x goes to infinity of negative 7x cubed plus 25x squared plus x plus 3. I'm going to learn from what happened last time and realize if I try to expand this as I did before, I get negative infinities and positive infinities, all kinds of infinities except for the number 3, and I don't know how to add those. So I'm going to try the same trick of factoring out that first term. So we'll have negative 7x cubed. We'll have a 1 here. We'll have minus 25 sevenths over x minus 1 over 7x squared plus 3 over 7x cubed. Oops, that last one should be negative. Right? So again, if you want to check that how this is factored, try multiplying this back in. In each case, we should get back what we, right? All these ones that were positive, we multiply net by negative, they'll become positive again. Notice there'll be a 7. If you multiply this out, if you distribute that 7x cubed, you'll see that we have the same thing if I did everything correctly. But now we're going to end up with the very same situation that we had up here. We're going to take the limit of each piece individually, each factor, right? This first piece, we're an odd powered function, putting in larger and larger x values, so they're going to be coming out very large positive, but there's this negative in front. We get negative infinity. In here, the same thing's going to happen that happened up above here. This 1, nothing happens to. And these all go to 0, right? They're in the same way this 4 over x did. We've basically got a constant times 1 over some power of x that we know is one of our rules. Those go to 0. So we end up with zeros, and our limit is negative infinity. Okay, let's look at this one. Here's that function. So we took the limit as we were going off to the right, and we see that it's doing just that, right? As we put in larger x values, it's just shooting down towards negative infinity. The takeaway from this little trick that we did, we can always do. Notice that the only thing that ended up mattering was what happened to the limit here. Because we're always, if we factor out that first term, we're always going to start with a 1. And everything else has smaller degrees. So when we factor that out, we end up with something over a power of x, and all of that disappears. That's what happened here. That's what happened here. So the takeaway is, if we want to take, if we have a polynomial, p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 on down to a sub 1x plus a naught. The limit as x goes to infinity is just going to be, all we have to do is look at that leading term, is equal to the limit as x goes to infinity of a sub n x to the n. And we look at those rules, that's a power function, and we made a set of rules for those up above. So for a polynomial, the only thing that matters in terms of its end behavior is that first term, right? The later terms are what gives us all these curves up and down near zero, right? All the little interesting parts of a polynomial. But out at infinity, right, these terms matter less and less and less as we get larger and larger x values, right? For instance, let's go back just for a second and look at this one up above, 7x cubed. Let's just think about the x cubed part. If we put in x equals 1,000,000 cubed is much larger than 1,000,000 squared. In fact, it's 1,000,000 times larger, right? So even though 1,000,000 squared is very large, it's not even close to 1,000,000 cubed. It's a 1/1,000,000th of 1,000,000 cubed. And then x is 1,000,000 times smaller. So these other terms, though they are huge in comparison, are inconsequential. And these massive numbers that come out of here drown everything else eventually. When you're small, right? And then the other thing is these coefficients don't do too much either, right? 1,000,000 cubed times -7, negative 7,000,000 cubed versus 25 million squared. There's still this huge discrepancy between the sides. You can play around with the calculator for a while to see just how big these numbers are. And even though they're all big, ones are the leading terms are really big in comparison. Eventually, when we put in 2, the same thing doesn't happen. Now all of a sudden, when we put in 2, this 25 does a lot because we have 8 times -7 and we have 4 times 25. Now all of a sudden those coefficients matter. But when we get billions and millions and trillions and all that stuff, those don't matter too much, and that first term will dominate, okay? And so we can always find the limit of a polynomial by just looking at those rules we developed above for power functions and just looking at the first term. And the same thing applies if we're going to negative infinity for some polynomial. We get just the limit of the first term, the leading term, okay? All right, let's stop there. Our next step, now that we've looked at polynomials, is we're going to start digging into rational functions. What happens when we start combining polynomials with using fractions and our rational functions, but we'll do that in the next one. Thanks, everybody. I will see you then.